So very good morning, everyone. So first of all, thanks to the organizing team for inviting me and giving me this chance to discuss about my work. And so today I'm going to speak about a few algorithm which is based on large scale data. And later on, I'll discuss a few applications. So let me first start with the outline of my talk. I'll start with the standard SVM and then what is twin SVM and the variants of SVM. And my focus essentially of this talk is to discuss theoretically development of the algorithm for the large scale data. So I'll start with the basics and slowly I'll move with the advanced version of these algorithms. So let me first start with the concept of support vector machines. Support vector machine is one of the most powerful tool for pattern classification and regression problems. And it has been emerged in 1995 by Wapnick and team. It emerged from research in statistical learning theory on how to regulate the trade-off between structural complexity and empirical risk. One of the most popular classifier is the maximum margin, one that attempt to reduce generalization error by maximizing the margin between two disjoint half planes. So it has been applied now almost all possible directions. One can see that people having background of engineering, sciences, healthcare, almost all people either they are using it as an applications or developing or using the advanced algorithm for their work. So as I mentioned that one of the most popular SVM classifier is maximizing the margin. So the basic idea is to find the optimal hyperplane or the best hyperplane between positive and negative samples, if we are talking about two-class problem. So let me first come with the linear case of support vector machine and with the basics that let us consider the training data points x1, y1, x2, y2, and so on, xl, yl, where xi are the inputs and the yi are the corresponding outputs. For example, here class +1 and class -1. So here SVM look for the optimal hyperplane or the best hyperplane between this positive and negative class samples. So as I mentioned that the first property of SVM is the maximizing the margin concept. So essentially, we need to find out the margin between two classes that is equivalently to the minimization of the regularization term, that is half norm of W square. So maybe one can see from this figure, suppose we have two class of samples, positive and negative classes. So, and we want to classify these two different types of data points. So one can see that the distance, we have to classify in such a way that the distance between these two class samples is maximized. So essentially, if you look at the mathematical part, so the data point should be from w dot x plus b greater than or equal to 1 and w dot x plus b less than or equal to -1. So we can take with a simple formula that this is coming out to be 2 upon norm of W. So we are essentially maximizing this distance 2 upon norm of W subject to the conditions that the data point should above this and should below this supporting hyperplane. So this is called hard margin SVM, or we can say linear SVM with no misclassification. So now further, there is a possibility that this data positive class data point may lie on another side, wrongly classify. So what we do, so that as I mentioned, that in the standard linear SVM without error, we are simply maximizing this distance to upon norm of W, subject to the condition that this data point should above this plane and below this plane. Now, if there is a misclassification, so then we have to penalize. We penalize those data points, and we add all those points in the objective functions. Let me show with this formulation. So, okay, one more important point, since we are maximizing this margin, that is, we are maximizing to upon norm of W. So essentially, we have to minimize W. So we are equivalently, we can say norm of W by 2. Or we can equivalently also say that minimum norm of W is square by 2. So the same thing we have written here, minimize this W subject to the conditions in this manner. But we have written that we have considered those kind of data points, which is there is some misclassification. So we add in the objective function those misclassifications, xi1, xi2, xi-l, and we sum up in the objective functions and then minimize. And here C is a parameter that controls the overfitting issue. Issues. So this is the basics of if we look at all possible directions. So this is a very simplest case here. So let me now discuss how to solve this kind of problem. And then later on, we will discuss how to move when the data is not linear. So since we have very simple optimization problem, we have an objective function in competitor. If we want to minimize a function subject to the equality constraints. So in this case, the necessary condition for a point x naught to be a solution such that partial order derivative of this object L times. If we then M will be on the set F1 G1 to G2X on whatever, and our constraints we have. So rest is same. So what happens if we have since? So now in case of inequality constraint, the Lagrangian multiplier should be positive if x naught is a solution of the constraint optimization problem, like minimization fx subject to the constraint that is gix less than or equal to 0. So then there must exist Lagrangian multiplier should be non-negative such that x naught must satisfy partial order derivative of the function fx plus sum of all constraints alpha 1 g1x plus alpha 2 g2x plus and so on number of inequality constraints at x equal to x naught equal to 0. And now we just put all the inequality constraints here. Now further, since we have an objective function and we have inequality constraints, So then the Lagrangian function will be the one, if we just write that is fx plus alpha times this gix. Or if we have more than one constant, so we just write alpha 1 g1x plus alpha 2 g2x and so on. So this is essentially called Lagrangian function. And then further we set its gradient to 0, and then we solve it further. For example, let me come back with this problem, and I want to solve it. So we have an objective function and we have inequality constraints with the non-negativity restrictions on this like variable. So what we do that first we construct the Lagrangian function. So Lagrangian function will be the one, first we have an objective function plus alpha times number of constant like alpha 1 g1 x plus alpha 2 g2x and so on equal to so this will be the Lagrangian function. Then we equate to 0. Then we take the partial order derivative, equate to 0, and then solve it. So we did in the same manner. First, we construct the Lagrangian function. And then we equate to 0 and take the partial order derivative with respect to w, b, xi. And using those KKT conditions, finally, we just, I skip two more steps, and finally we get these dual problem. So essentially, the dual problem is this is summation alpha I minus half summation alpha I alpha j yi yj xi transpose xi as subject to the constants alpha I yi equal to 0, and where alpha lie between 0 and c. So now what we observe, and important to note here, that the data points in the dual formulation appear in the form of dot product. You see this xi transpose xi. But since it's a linear case, it's quite easier to solve. It's straightforward to solve the problem. A simple system of linear equation, one can directly solve it. But what happens if we have a non-linear data? Or if we have a highly complex data, how to address those issues using SVM. So let me come with those examples. So we can start with the first. So we have in a real line, we have two different kind of data points, blue data points and red data points. So we can see that this is nice data. And we can just draw a line in the middle of, and we can say this is nicely classified. There is no problem. But what happens if we have this kind of data? Second example. So in the second example, we can see that this data cannot be classified linearly. So how to do that? So we cannot classify linearly in a real line in one dimensional. So, but what we see that if we map the same data in high dimension, means from one dimension to two dimension, from line to plane. So what we see, for example, from function fx equal to x square, we see that data points will move up. So when the data points will move up, so we see that we are able to draw a line between blue data points and red data points. So this is just an intuition that the data points which were not linearly separable in one dimension can be linearly separable in higher dimension. Okay, so this was a very simple example. What happens if we have this kind of data? So we have within the circle, we have red data points, and outside the circle, we have blue data points. So how to classify this kind of data? So the concept is coming here, the kernel trick and those Mercer theorem. I'm not sure how many of you are aware of it. So the basic idea is that we transform this data, this left side data, with a map phi from lower dimension to high dimensional space. Or we can say that the original input space can always be mapped into some high dimensional space such that the data is linearly separable in some dimension. So how to do that? We have just map phi from Rn to Rm. So suppose Rn to Rm, and where m is greater than n. Okay, so we go with the same idea that we map in some high dimensional space such that the data is linearly separable. So now the question arises in our mind that what will be the nature of phi, in which dimension the data will be linearly separable. So those answer will come when we are going to solve the problem. So let me go and see. So first we have seen that if the training data are not linearly separable, so to enhance the linear separability, the original input space map into high dimensional space, as we have seen. So this is essentially called feature space in literature. So if we look at the linear SVM problem, so and we have seen that the data points in the dual formulation appear in the form of dot product, that is xi transpose xi. So this is just a number, right? So now, okay, let me just highlight this note, and the answer essentially will come when we solve the nonlinear problem. As long as we calculate the inner product in feature space, that is, we are talking about nonlinear case, we do not need the mapping explicitly. Means we are talking about phi and nature of phi. So even we are solving the problem in high dimensional space, even though we do not need to know the nature of phi. So let me first come with this function k. So k is defined like phi transpose phi. So it is called kernel function. The concept essentially is coming from the Mercer theorem. So if you are more interested, so please go and see more about the Mercer theorem and those concepts. And this is based on one fundamental theorem. So how to do it and how we say this is k. K is just represented as phi transpose phi. So, and we already know that phi is a nonlinear map, or we can say that phi is a map that transforms the input data to high dimensional space. So this is just an example that we have this phi and we write phi transpose phi, so it can be written just a number. So if we define the kernel function, so there is no need to carry out the space explicitly. So now this use of kernel function to carry out phi explicitly is known as kernel trick. So now moving forward, so and it will give the answer of those questions I raised. So let me start with the formulation of a nonlinear SVM. So what we are doing that if we remember the SVM linear formulation, the only difference is that in place of xi, we are just replacing with a phi xi. And as I already mentioned, that phi is simply a map, or we can say a nonlinear map or function that transform the input data into some high dimensional space. Okay, so how to solve this problem? So we go exactly on the similar lines that we first construct the Lagrangian function, equate to 0, take the partial order derivative with respect to w, b, xi, alpha, and beta, and then we got those values, and then finally we put again, and then we get this dual formulation. So now from this is very important to see that if we see that we are solving nonlinear SVM problem, that the data is highly complex, and we are using the concept of SVM kernel to solve this problem. So what we see that when we are dealing with a nonlinear SVM formulation, when we solve this dual formulation, we see that the data points appear again in the form of dot product, that is phi transpose phi. So phi transpose phi is nothing but it's a kernel function, it's simply a number, and there are many kernel functions available in the literature that can be solved directly. So, so further we simply write some k, and then we just use either Gaussian kernel or polynomial kernel, sigmoidal kernel. So many kernel functions are available in the literature. One can go and directly use it. So this is the beauty of support vector machines to handle highly complex data linearly. So I hope that this concept is clear for many of you. So, so since those concept was developed in 1995, around 20 years ago, so and later on, a lot of improvements have been developed. For example, Mangasarian and his co-workers propose a non-parallel SVM called generalized eigenvalue proximal support vector machine. So in this approach, data points of each class are proximal to one of the two non-parallel planes, and the non-parallel planes are eigenvectors corresponding to the smallest eigenvalues of two related generalized eigenvalue problem. And then I think a lot of work in the directions was developed by the researchers, and in 2007, another concept came by Jayadeva and team, and that was published in IEEE PAMI, called twin support vector machines. So it is a computationally efficient model. It performs classification using two non-parallel hyperplane instead of a single hyperplane. So that we usually say this is approximately 4 times faster than SVM. So the idea of twin support vector machine aim at generating two non-parallel planes. Let me go with this. So this is a geometrical interpretation of twin support vector machine. So it aims at generating two non-parallel planes such that each plane is closer to one of the two classes and is as far as possible from the other. So the formulation of twin support vector machine is very similar with standard support vector machine. However, the algorithm of twin support vector machine is different in one fundamental way. So we can see, and we already have seen SVM algorithm, and now this is twin support vector machine algorithm. So in twin support vector machine, we solve a pair of quadratic programming problem. So we can see that we have one QPP and we have another QPP. So essentially in support vector machine, what we have seen that quadratic programming problem has all the data points in the constraints. But in here twin support vector machine, they are distributed in the sense that patterns of one class gives the constraint of the other class and vice versa. So this strategy of solving two smaller size quadratic programming problem rather than solving a very large QPP, it makes twin support vector machine fast than conventional standard support vector machine algorithm. So we can even discuss more about this algorithm. So we can see that we have two smaller size quadratic programming problem. So this algorithm finds two hyperplane like we have seen in this figure, one for each class, and we classify points according to which hyperplane a given point is closest to. So if we look at this mathematical part, this is the first term or the first optimization problem or objective function of this is the first term is essentially the sum of square distances from the hyperplane to points of one class. Therefore, minimizing it tends to keep the hyperplane close to points of one class, say class plus one. And the constraint require the hyperplane to be at a distance of at least one from the other class, say class minus one. And the second term is essentially the sum of misclassified data points. And here C1 is as same as is a parameter that control those overfitting issues. So in the same manner, we have another problem for the another class. So here A is corresponding to data points of class plus one, and B is corresponding to class minus one. Okay. So essentially, twin support vector machine is comprised a pair of quadratic programming problem such that in each QPP, the objective function correspond to a particular class and the constraints are determined to a particular are patterns of another class. You can see easily for each QPP. So essentially, we see that the complexity of twin support vector machine is better due to solving a smaller size of quadratic programming problem. If we look at its running time or complexity, so for example, if we have, for example, number of samples is m, right? So, and in the case of SVM, the complexity will be big OM cube, right? And if we see for a case of twin support vector machine, for example, 50% data points class plus one and 50% data point class minus one. So, for example, so total samples is m, so m by 2 is corresponding to class plus one and m by 2 corresponding to class minus one. So in this case, the complexity will be, that is 2 times m by 2 cube. So if we compare with the SVM, so this will be m cube divided by 2 times m by 2 cube. So that is coming out to be 4. So 4 times faster than SVM. So this is not the exact case. So this is the case when data is nicely distributed. So sometimes we say that data is usually data points are distributed in imbalanced way. So, so in that case, the classification, this running time may be less, maybe more, but sometimes we see that even most of the numerical experiments, if we look at twin SVM or least square SVM or any variants, so twin SVM variants is usually faster than SVM, sometimes 10 times, sometimes we see that 20, 30, 40 times faster than SVM. So when we solve this problem, twin support vector machine, we just go with the same way that we construct the Lagrangian functions, take the partial order derivative, equate to 0 with, and with respect to WB and so on. And finally, we got these dual formulations and we get WB. So what we observe that the dual formulation, that the matrices appear H transpose H or G transpose G. So they are not always invertible. So you see that there is square matrices, but they are not, they may not be invertible. So, so what we have done, what authors have done in this paper, they have they have added extra regularization terms. The optimization problem is invertible. So, so this is one of the drawback of this algorithm. So, but later on, I think in 2011, Shao and co-workers developed another variant called twin bounded support vector machine. So what they did, so they essentially incorporate extra regularization term in each objective function. So due to that, due to incorporation of extra regularization term in the objective function, so those issues are automatically resolved, and this is coming out to be like H transpose H plus some C3I, and here is also G transpose G plus C4I. Some C3 and C4 are some parameter. So then we tune the parameter. So, but in this case, we have fixed delta. Delta is some fixed number. So, due to that, the performance will go down. So, so due to incorporation extra regularization term in the objective functions of both the problem of twin SVM. So, the new algorithm called twin bounded SVM is theoretically more sound than this twin SVM algorithm. And numerically also, we have seen the significant differences. So, but what we see at the same time that one of the drawback essentially of this twin SVM or twin bounded SVM or other variants of twin SVM, that whether this is where whether they improve the theoretically after incorporating extra regularization term, means the matrices is automatically invertible, or to make to introduce delta to make the matrix invertible. So essentially, we have to calculate the matrix of the inverse. So if we are calculating the inverse of the matrices and the data is large, so then this algorithm may not be as useful for the large scale data. So how to address those issues? So we will discuss that. So before moving that, let me first discuss very nice algorithm called least square version of twin SVM. So what they have done essentially, so they just replace inequality with the equality constraint, and they also replace one norm of the slack variable, error variable, with the two norm of the slack variable. So these two small change, but fundamental change, it help us to solve the problem nicely in a simpler manner, that we are simply solving system of linear equations rather than solving QPP. And no need of any optimization toolbox because they are simply system of linear equations. So, and people who are looking for fast algorithm, this could be one of the one that one can use it. So, but we are going to now, but in this case, this is extremely fast even than twin SVM. But if you go for the solving problem and you want to calculate W1, B1, so we are again need to calculate the inverse of the matrices. So those issues again will come, right? So now my intention in this talk is to discuss the points that overcome those issues in the formulation. So let me first start with one algorithm which is really very efficient called improved twin support vector machine. It came in 2014, and the major advantages are that they simply reformulate the primal form of twin support vector machine formulation in such a manner that the algorithm is feasible for the large scale data. So it's again very the major difference, the way of solving is the main beauty of this algorithm. And another is they minimize the structural risk that results in improved generalization performance. And the most important, that they reformulate the algorithm in such a manner that it avoids the computation of the matrix inverses. So it will help us to implement the algorithm for the large scale data. Now, another very important property is it doesn't need to deal with the kernel generated surfaces. If you look at in pin support vector machines for the kernel non-linear algorithm, so this is not same as if you just replace non-linear kernel with a kernel. So, and that's why it is mentioned that it is directly on the lines of SVM that incorporate the kernel trick directly into the dual problem. Means we simply write A in place of A just phi A. We can see that we are just discussing nonlinear formulation of ITSVM. So you can see that first they incorporate extra regularization term, and then for the kernel prick they just use A with the phi A and B with the phi B, and rest remaining the similar way. And but the most important way that what they have done, they have considered this constraint in solving the dual problem. So this is the beauty of this algorithm, that they have considered this Lagrangian functions and they have considered as a constraint. Like this is phi A W1 plus E1 B1 equal to eta 1. Okay. So, and when they solve it, means use those KKT conditions, and finally what they are getting this W1 B1. So when we are calculating this W1 and B1, so what we observe here that W1 and B1, they are free from the inverses. And when we see the dual problem, so this is the dual formulation. So, and this is a matrix Q cap or Q tilde. So Q tilde is also free from the inverse. So this is the beauty of this algorithm. Now one can see and implement on the larger scale data, and it works very nicely on large data sets in comparison to the baseline QueenSVM algorithms. So let me now move forward to discuss another algorithm called large scale pinball pin support vector machines. So let me first discuss some background that in order to make the model formulation suitable for large scale data, we formulated the problem in this manner that, as I mentioned, that is tune bounded SVM, that is the fourth one in 2011 paper. And this is pin GTSVM. This is pinball for the twin SVM. So the property of those algorithms are retained while ignoring the calculation of the large matrix inverses. So these changes are the introduction of a regularization term and the addition of an equality constraints, similar to the previous algorithm, ITSVM. So since we are using this all the properties of pin GTSVM, so in pin GTSVM we introduce this pinball loss functions. So since pinball loss is already present in this formulation, so our proposed idea, our proposed formulation is insensitive to noise, and it is more stable for resampling. So this is the property of the pinball loss function, that it is insensitive to noise and more stable for resampling. So essentially in pinball loss functions, rather than giving penalty for the wrongly classify in pinball loss, we also give penalty for both wrongly and correctly classified samples. So you can see that this is really a very nice loss functions. Please see, and one can use it. Now, the third is LPTWSVM. This formulation ignore the computation of large matrices, matrix inverses, it leading or it help us to develop the algorithm for the larger scale data. And another very important property of this algorithm that we incorporate the kernel trick directly into the dual problem. And this SRM principle is implemented, and that improve the performance of the algorithms on the data sets. So more informations about this can be found in a paper published in Machine Learning, Springer. So if you're interested to read more, so please go through this paper. So what we have done, that we reformulate the objective functions of twin bounded SVM by incorporating the pinball loss functions. The reformulation can be written in 27 and 28. So what we have done, so essentially we keep this when we are constructing the Lagrangian functions. So we are considering it as a constraint. Okay, and this term we have added due to this pinball loss functions. So if you see that when tau goes towards 0, so this whole constraint is reduced to xi greater than or equal to 0. So essentially this whole formulation, when tau is tending to 0, so this whole formulation goes means it reduced to essentially twin bounded SVM algorithm. So one can say that twin bounded SVM is a particular case. Even twin SVM is also a particular case of this algorithm. Okay. So I hope that this is clear. Now, I'm moving forward to discuss the solution of this problem. So I'll move on the similar lines that first we construct the Lagrangian functions. So in the construction of Lagrangian functions, I also considered as a constraint, equality constraints, and the Lagrangian functions, then take the partial order derivative with respect to WB, alpha, beta, whatever, alpha, gamma, and all. And then we solve it and finally put again here and get the dual problem. So the dual problem is coming like this. So you see 37 and 38. So the matrices appear in the dual formulation, that is Q tilde, as free from the inverse. So this is the beauty of these algorithms, that since we are doing on the same manner, our way of working is slightly different, that can handle the larger scale data. So in this case, you can see that the invertibility issues is completely removed. So, so we do not need to compute the inverse of the matrices. So for example, if we say the dual formulation of another part is also that free from the inverse matrices, and then we solve this similar to pin GTSVM, means when the decision function is similar to the previous algorithm. So now moving ahead, this is a nonlinear function, a nonlinear part of our formulation. So in nonlinear part, so we simply transform this data, transform in this manner that we just replace x with phi x, y with phi y. or A with phi A, B with phi B. So essentially, this is called equation 41 and 42. So they are essentially the primal form of the nonlinear linear programming twin support vector machine algorithms. So even though if you see here that if you put tau is 0, so this since it is xi greater than or equal to 0, so this algorithm is essentially we can go to the TBSVM algorithm. Means if the kernel taken appropriately, journal kinetic surfaces. So here we incorporate kernel trick directly. So as I mentioned here that we have transform x equal to phi x, x is Hilbert space. So now we can see here 41 and 42 and 43 and 44 here. So these dual problem can be seen that the matrices appear here in 43 and 44 are free from the inverse matrices. So all variable constants and notations are similar to those from the linear case. Once we solve this 43 and 44, so new data samples is assigned to given class based on the distance. So let me discuss a few numerical experiments, whatever we have done in the literature, especially for this paper published in machine learning. So please see for more details. I'll discuss only a few experiments. So here we have considered NDC data sets with size from 20,000 to 90,000, with number of features 32 for all. So what we see from this table that we have implemented these 4 algorithms on the same machine with the same configuration. And the first 3 algorithm is also the twin support vector machine variants. So due to the invertibility issues in these 3 algorithms, when the data is becoming large, so they are essentially filled after this 70,000 samples. So on our machine. So if we have even suppose if we have high computational machine, so maybe it can work up to 2 million. So but may fail after 2 million these baseline algorithm and can work our proposed algorithm. So at the same time, we also have tried to implement our algorithm for a smaller size data just to check whether our algorithm works well not only for large data, but smaller size data also. So one can see that average accuracy and average rank are better than the baseline algorithm for both linear and nonlinear cases. So here, this is a nonlinear case, we have considered Gaussian kernel. Okay, so now let me discuss another algorithm. Possibly this is the last algorithm, and I will discuss only the few applications after that. So let me first discuss the motivation behind our new algorithm. So we analyze the baseline twin support vector machine and robust fuzzy least square twin SVM for class imbalance learning. These 2 algorithms, so there are few shortcomings. So both the formulation involve matrix inversion, which act hindrance in applying it to the large data sets. And both formulation implement empirical risk minimization principle and assume that matrices appear in the formulation are always well conditioned. However, in the real problem, this assumption may not satisfied and hence leads a lower performance. And this is very important, that twin SVM and robust fuzzy least square twin SVM for class imbalance learning say they need to solve linear and nonlinear case separately, as a nonlinear case is different from the linear case when linear kernel is used. So with this, we proposed an algorithm, and the name is large scale fuzzy least square spin support vector machines for class imbalance learning. So let us first discuss a few advantages. So the first advantage is that we reformulate essentially on the similar lines as I started with the IT SVM. So we reformulate in this manner so that our algorithm is feasible for the large scale data. And it minimizes the structural risk that results in improved generalization performance. And it also avoids the computation of matrix inverse, while the other given baseline models need to calculate the matrix inverse, which is infeasible for the large scale data. And next is that it doesn't have to deal with the kernel generated surface, unlike the given baseline model of twin SVM. So they are essentially incorporate kernel directly into the doer problem. And finally, after incorporating this fuzzy membership, it handles the class imbalance problem. So those things we are going to discuss now. So one can see our proposed algorithm. So this is called large scale fuzzy least square twin SVM for class imbalance learning. So it was published in 2022 in IEEE Transactions on Fuzzy Systems. So I'll discuss only the nonlinear part. So more details are available in this manuscript. So please go through this if you are really interested to work in this direction. So it is publicly available, so you can see. In case you need it, you can drop an email to me or my student, so we can share. So what we are doing that first is we incorporate an extra regularization term, and this is we are just putting eta1 transpose eta1, and eta1 we just kept it as a constant, and we have S1 and S2 are fuzzy membership weights, and we have done with the slack variables, xi1 and xi2 error variables. So essentially, we are giving appropriate weights to each data points. So it helps us to classify more efficiently. So, and how to do that for the fuzzy membership functions for the positive class data points, we are simply say fuzzy membership is 1. And for a negative class samples, we have just writing Z plus Z, this is this. So here Z is nothing but this is 1 upon 1 plus IR. IR is imbalance ratio, and D1 and D2 represent including distance. And D is a distance between class centroid and negative class maximum distance from centroid given by R2, and 0 is essentially the exponential scale of the fuzzy membership function. So now we have this formulation and we want to solve it. So first we construct the Lagrangian function, and we are just keeping this as a constraint. So as I mentioned in the previous previous algorithm, that it helps us to work for the larger scale data. So we are adding as a constraint. And when we solve it with respect to alpha, beta, gamma, and so on, so we solve this problem, and we can get this W1B1 and W2B2. And we can see that these are, again, efficiently we are solving. Essentially, it is coming as to inverse, so but this is the diagonal form, this fuzzy membership weights, so it will not impact. So we are efficiently work for the larger scale data in this formulation. Now, how to solve this dual formulation? So first, what we are doing, we are using SMO algorithm. So first we have to rewrite in the format of SMO. So we just did some background, and finally we write the formulation in this manner: maximum minus half Z transpose Q tilde Z minus V transpose Z, and informations are available about Z is a vector of length I, and Q tilde is a positive definite matrix of size L cross L, and V is a vector of appropriate dimensions. So essentially, we have used a SMO algorithm that was proposed long back in 2003 by Kirti and Shevde. So we are just using it, and finally we just use it, this algorithm. So now I think I'm almost done, and I need to discuss a few applications and how we have implemented on UCI benchmark database. So those things I will discuss. So let me first discuss with some applications of this algorithm. So in this work, we have used Alzheimer data. So and it is publicly available on ADNI website, and we have considered around 817 SMRI images, and we have distributed that MCI, ADN, CN subjects with this 228, 398, and 187 images. Due to that, 4 images failed to process pre-surfer pipeline. So let me just discuss a few results of this manuscript of this paper. So you can see that based on this Alzheimer disease data, so the most difficult one with MCI versus AD. So we can see that the algorithm, our proposed algorithm is performing very well. We see that average accuracy is coming 0.68, that's 68%. And the second highest is 65. So around 3% difference, significant difference. And we also have seen the average rank also, and overall win tie loss. Means overall 7 times win and 0 times a tie and loss 2 times. And now we also have considered the training time of the proposed idea and the baseline algorithm with the imbalance ratio, whatever we have considered, and we see that all the baseline algorithm failed on those setup we have considered for the baseline and the proposed one. And however, the proposed algorithm works very well. Now, I have discussed a lot about twin support vector machines. So this twin support vector machine started in 2007, around 17 years ago. So a lot of improvement have been done in the recent years. So you can see that with the percentage that the people working mostly on least square twin SVM, multi-class twin SVM, and several other improvements, including fuzzy, pinball loss, sparse version, tune parametric version, projection version, clustering based, semi-supervised, and it has been applied in several directions. you can see that it's mostly apply on Alzheimer's disease and EEG signal classification, and also human activity recognition, text categorization, intrusion detection, image denoising, cardiac disease, speaker recognition, and several other applications. So please see this paper. We have written a very detailed review, comprehensive review on twin support vector machine. It was published in Annals of Operation Research in 2022. So one can see this paper for more clarity. We have given our future possible directions, our recommendations. So now, this is the deep learning for brain age estimation. We have written a review paper. Please see that this is very interesting work if you are working in this domain. So during our writing this manuscript, so there were only 35 papers in the literature. So we have a lot of scope to work in this direction. So in this work, we categorize brain age estimation model based on deep learning architecture. And we classify deep learning architecture based on slice-based or voxel-based input data. And we examine modality, size of data, performance, and data sets used. And we have enumerated several challenges and directions. You can see that explainability in deep learning, as since we know that there is no information about input-output relationship. So explainable AI can explain the relationship, which will be very helpful for doctors to take decision. So this we have just used several like feed-forward neural network, CNN, VGGNet, ResNet, and several other deep learning architectures. So, and you see that we have possible directions that how to reduce the computational complexity and how to see the specific brain region and brain age difference, which is very, very important. The reason is that brain affected due to several neurological disorders like Alzheimer, Parkinson, and so on, and how to integrate the multimodal data. So there are a lot of scope. It's it is now a lot of open problems we have. We can work in that direction. So more informations about this and possible future avenues is available in this paper published in Information Fusion in 2023. So please see this one. And another very important that this is the recent work that published in Nature Mental Health. So especially title is Ensemble Deep Learning for Alzheimer's Disease, Characterization and Estimation. So we know that Alzheimer's disease is a neurological disorder disease. So, and it characterized by accumulation of amyloid plaque and neurofibrillary tangles in the brain. So mostly Alzheimer's disease is mostly common in individual when age is 65 or more, and it causes cell damage and death in critical brain areas. So it impacts memory and cognitive functions. So according to the recent report, around 50 million people were affected by this disease, and it is expected to triple by 2050. So early detection and diagnosis is very important to save the life of the people. So Alzheimer's disease manifests through various symptoms like affecting that is cognitive functions, recognizing these there are several signs like challenges in planning for solving problems, confused day with night, like inappropriate use of words, mood change, memory loss, loss of vision, and several other symptoms of this Alzheimer's disease. So essentially, we have we have written this review, this paper just to encourage researchers to work in that directions. This is a very growing area of ensemble deep learning that can be very helpful for Alzheimer's disease diagnosis and detections. So this is another, we have seen that we have shown some figures for homogeneous ensembling approach and heterogeneous ensembling approach. So please see this paper. This is very recent. I think just 2 months ago it was published and publicly available. I think I can stop here and so this is just an announcement that the last date submission deadline is 22 July of the conference ICONIP. It will be in Auckland, New Zealand from December 2 to 6. So please submit your papers in this very good conference. So all of you are welcome to submit your work. I'm one of the program chair this year. Okay. So I think with this, thanks to my funding agencies, thanks to my students for their excellent contributions. So thanks. So maybe I can share my email ID, possibly, yes. So my email ID is here. So yes, so I can take a few questions and then.
Many of the participants have any questions, please.
Question is basically that we are computing eigenvector or eigenvalue for PCA also. So, sir, what is the difference between SVM and principal component analysis here?
In what sense?
Sir, we determine different linear subset in PCA also. So that is why I'm asking that, sir, what is the difference between SVM and PCA to find out the linear subset?
Your question is unclear to me. So PCA usually used to reduce those dimensions, right? So in what way you are asking is unclear to me. If you can specify your questions in more detail, that will be helpful. So usually PCA is just a dimensionally reduction technique, right? Usually used people in statistics, machine learning, and
If anyone else is there to ask any question, please. So those who are available online, if you want to ask any question, You can unmute yourself and ask the question. Otherwise, you can also type a question in the chat box. All those participants who are available online, you can also raise your question. Either you can type your question on the chat box, or else you can unmute yourself and ask the question directly.
Sir.
There is a question from Avinash Gopal. You want
Sir,
to know
whether the
whether
pinball loss function is similar to quantile function, or is there any relationship between them? And function is why the word pin.
Yeah, quantile. Yes, yes. This is the relevant. So they use the concept of quantile function to develop this pinball loss functions. So essentially in the pinball loss functions, so what they are doing, if you see, I think I could not specify those loss functions. So if you have seen the tau, I have mentioned in the constraints that we have one term is tau, and where tau is belonging to some interval 0 and 1. So when this tau goes towards 0, so essentially, so if I say in general for the pinball loss functions, so the property in this manner, so usually what we are doing, that we penalize those data points which are wrongly classified, right? So, and in pinball loss functions, what we are doing, we are penalizing to both the data points, which is either wrongly classified or correctly classified in such a manner, so that so it helps us to give the penalty specifically whether it is too far or it is too close. So the performance is really very good when we introduce this loss functions in any this SVM or twin SVM algorithms. So I think the first it was introduced by Sequence and SVM algorithms, and we were the first to introduce in the original twin SVM algorithms. So the only this difference that we just give the additional penalty on the correctly classified data points. Or you can also say that this pinball loss can be regarded as generalized L1 loss function.
Is there any more question? Offline, online, all participants. Do you have any question, please ask. Otherwise, there is one more question. What are the main features to give input for the DL models for the brain image estimation? There is a second question from the online participant. The question is, what are the main features to give input for the DL models for the brain age estimation?
So in this case, what happens, we have the publicly available data that we have taken from our collaborator from Canada. So we are considering simply as a input MRI images of the brain age, and then we initially pre-process those data so to make all the images in the uniform manner, and then we give those input to the DL. So if you look at for the brain age, so very recently, I think just a few weeks ago, we have written a comprehensive evaluation specifically for brain age data. So, and we have given our conclusion and recommendations that which deep model can be helpful for this data. So if you are interested, Mr. Avinash, so you can write to me, I can share that paper.
Thank you, sir.